Let's do problem number 78. A painter climbs a ladder leaning against a smooth wall. At a certain height, the ladder is on the verge of slipping. A. Explain why the force exerted by the vertical wall on the ladder is horizontal. B. If the ladder of length L leans at an angle theta with the horizontal, what is the lever arm for this horizontal force with the axis of rotation taken at the base of the ladder? C. If the ladder is uniform, what is the lever arm for the force of gravity acting on the ladder? And we'll get to D later because that's not our concern right now. But A wants us to know what is the force exerted by the vertical wall on the ladder. Why is it horizontal? Why is this force horizontal? It's actually pretty simple. It's because they tell us it's a smooth wall, so there's no friction. This is a simple diagram of the problem. I'll draw another one real quick. So this is your ladder. There are other forces here, but let's just focus up here where you would have normal force pointing out to the right and your friction going up. You would have friction going up, but since the wall is smooth, there is no friction. And so the reason why there is a horizontal force is because it's the only force and it's in the horizontal. So you can write something like, since there is no frictional force upwards, there is only the horizontal normal force to the right. Write something similar to that, it should be just fine. So B wants to know if the ladder of length L leans at an angle theta with the horizontal, what's the lever arm? So let's just draw a bigger diagram for this. So they tell you that's length L, and they tell you that this is theta, and they want to know what is the lever arm. So what is a lever arm? Well, before we go back to this problem, let's talk about an example that the textbook gives you about a lever arm. So let's look over here at these three doors that the textbook uses to demonstrate the lever arm. On the third door, you can see, well, okay, like before that, the context is, there's a door and the force is being applied, right? So over here, since the force is to the right, the door is not going anywhere. And down here, the force is at an angle, and they want, it's kind of like the problem we're doing right now. They're wanting to find out the lever arm. So in order to find out the lever arm, you want to find out the vector that is perpendicular to the force that the problem is talking about. So in this case, the force of the door is here, so what you would do is find the vector that is perpendicular to this force. So what the book did here is they extended it and they found it perpendicular, but it has to meet with the pivot. So you would, once again, you want to find the line that is perpendicular to the force and meets at the pivot. And Mr. Greenberg mentioned something in class that it's r sine theta. And let's go back to the problem. We're going to do exactly the same thing, except for this one, they talk about the horizontal force right here. They're talking about the horizontal force. So that means they're talking about the normal force that we were working with earlier. So let's actually try the normal force again. So they want to know the lever arm. So this is the force that we want, and we want to find the perpendicular line to this. So we're going to extend it. It has to meet at the pivot. The pivot's at the base, and so perpendicular you would just go up to that force. It's perpendicular to the force, and they want you to find the lever arm is this line and not this line, because you already know there's no force. The only thing left is this. So what is this in terms of L and theta? Well, it's L sine theta, because this is the same as this. And if you want to know what's that, well, you can tell it's opposite and hypotenuse, so L sine theta. That's your answer for B. And C wants you to do the same thing, except the force, instead of like using this force, they want you to use the force of gravity on the ladder. So let's draw the diagram one more time. This is again your L, this is your theta, And so the force of gravity on anything that's like a board, or in this case a ladder, it's going to be the center of mass, which is right here, and it'll be pointing straight down. This is the force of gravity acting on the ladder, and since center of mass is in the middle, this would be L divided by 2, and this would be L divided by 2. And so in order to find a lever arm, this is the force that we're talking about, and we need the line or the vector that is perpendicular to this force and meets with the pivot. So this one should be a lot easier to see. It's right here, extended a little bit, and it's perpendicular to the pivot, which is right here. And you already know this one too, or you want the expression for this line right here, which will be L over 2. It would be opposite, no, it will be cosine, because when you use this, it would be over 2 cosine theta adjacent in the hypotenuse. So this is your answer for B. No, this is your answer for C. L over 2 cosine theta. Alright, let's work on part D. This time we are going to solve for the maximum distance a painter can climb up this ladder without it slipping off. So let's draw the diagram for this. Here's the ladder. This time they tell you that the ladder is 4 meters long. So it's 4 meters long. Let's draw forces. You know that force of gravity on the ladder is right in the middle, going straight down. And they tell you that the mass of the ladder is 30 kilograms. And since the force of gravity down is weight, is mass times gravity, let's just, write 30g to make things a little bit easier. We don't know. We want to find out, if a painter was going up, how far could he go before the ladder, topples down or something like that. You don't really know where this painter is, but let's just say he's up here. They tell you that he's 80 kilograms heavy, and so let's just represent that as 80g down. And alright, and the coefficient of friction is 0.45. You know that there's a normal force going up here. We call that N1. There's a frictional force going to the left. And from earlier, you already know that there's a normal force here. We'll call that N2. So how do we find out, this distance over here? How do we know? How can we find this out? Well, let's just start summing our forces in the x direction and the y direction, and then summing our torques. Alright, let's do the x direction. Let's define real quick. What is positive y, and to the right is positive x. So, since positive minus your negative, so normal force 2 minus your friction, but let's just write friction as mu n, make things a little bit easier. The sum of forces in the y direction now. In the y direction, you have your positive normal force 1 minus your weights, so minus 80g minus 30g should give you 0. Now the sum of torques. We need a little bit of room here because we're going to continue those later. The sum of torques. So let's look at this diagram. This normal force would be pulling this ladder, clockwise. So the normal force in this case is our negative torque, and the weight will be pushing this ladder counterclockwise. So that's your positive torques. So let's write that. Your torque is R force, sine theta. So you don't know how far the painter needs to go up yet. So that's just going to be R, and that's what we're going to be solving for eventually. Then the force of gravity downwards for this painter would be ATG. And what's the angle? I forgot to write it earlier, but this angle right here is 53 degrees. And if this angle down here is 53 degrees, this angle up here is 37 degrees. And using the rule of corresponding angles, you can shift this angle down, so both of these would be 37 degrees. So back down here, R, F, sine 37 degrees. Sine 37 minus, no, this is your positive torque, so plus your other positive torque, which is the force of gravity acting on the ladder. This time it's center of mass, so it's in the middle of this 4 meter long ladder, so R would be 2 meters. times the force of gravity, 30g, also sine 37, as you can see, because the angle transfers down, and minus your negative torque. Your negative torque would be this normal force. Well, first, since the ladder is 4 meters long, 4 meters is your R, your force is your normal force, sine, not this angle, because the angle that you want to use for your torques is always in between the force and R. In this case, it's right here. It's in between the force and R. So 53 degrees, alternate angles. Sine 53 equals 0. So when we look at this whole thing, we don't know R, but we can actually solve for normal force 2. So let's just go back to our y. So with the y, we can actually solve for normal force 1, so that we can go back here and solve for normal force 2. Because in order to solve for normal force 2, you're going to need the first one. So let's do that real quick. It's really simple. It's just 80g plus 30g. So normal force 1 is 1078 newtons. So going back to summing the x direction, N2 equals your coefficient of friction times N1. So that would be 0.45 times 1078 newtons. That will give you a normal force of 485.1 newtons. So let's go back down here and start plugging stuff in. So for this R part here, since we don't know R, I'm going to do 80g times sine 37 first. Let me just show what I mean. 80 times 9.8 sine 37 gives you 471.82 newtons. No, not newtons, but what you want to do with this number is go back here and do this. 471.82 R. That's how we want to represent R right now. And then later you can divide it later. You should know what I mean. So let's continue. 30 times 9.8 sine 37 gives you 353.87 minus, here you just find your normal force, your second normal force, so all you have to do is multiply together and you will get minus 1549.67 newtons. Don't forget that newtons over there, equals 0. Get all terms that are not R to the right. So 471.82 R equals, just bring it over, you'll get 1195.8 newtons, and R gives you 2.53 meters. That's it. So this painter can only climb up 2.53 meters before the ladder would slip and fall. And that's it for this problem. Okay, quick note about B. Some of you might have been wondering, when you talk about what is the lever arm for this horizontal force. Well, there were two horizontal forces, right? Not only do you have this normal force, you actually have a friction force here, right? Because after doing, part D, this is, we know that it's a friction force. So how do we know that it's only the normal force and we're not talking about this when we are, trying to do the lever arm? It's because, we set the pivot here. So any forces here just don't matter. Yeah, that's it. I forgot to mention that earlier. But yeah, that's why we're using this normal force as our horizontal force, because that's the only one here. This friction force doesn't matter because we have a pivot. That's it.